Hello and welcome to today's ACM 6-Off webinar. This webcast is part of ACM 6-Off commitment to provide value to its current and future members. The ACM 6-Off webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. I'm Robert Dyer, Assistant Professor at Bowling Green State University and member of the 6-Off Executive Committee, and it's my pleasure to welcome you today. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R on a Mac, or refresh your browser on mobile devices. Or you can close and relaunch the presentation. Control Volume adjusts the master volume on your computer. If you have questions during the webinar, please type them into the Q&A box at any time during the webinar and click the Submit button. At the end of the presentation, we will have time to respond to questions. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Today's presentation is Analysis Techniques Especially Suited to Software, the final part in the series on Fundamentals of Measurement and Data Analysis for Software Engineers by J Frailey. Dennis is a retired principal fellow from Raytheon, where he worked on software metrics and safety-critical applications. He also served for over 40 years as an adjunct professor of computer science at Southern Methodist University, the University of Texas at Austin, and the University of Texas at Arlington. Dennis is an ACM fellow and an IEEE senior member. He was the 2008 recipient of the ACM Lifetime Achievement Award in Computer Science Education, and the 2013 recipient of the IEEE Computer Society's CSEET Nancy Mead Award for contributions in support of software engineering education. Dennis, without further ado, take it away.
Okay, thank you. Okay, we are here. Those of you who've been with me for all four parts, in the past we have spent a lot of time talking about very fundamental ideas such as statistical distributions, various other important characteristics like the scales. And we also spent a lot of time, in effect, saying, here's why you can't use certain statistical techniques because of the fact that the data were not well behaved or various other problems. For example, the data weren't in a normal distribution. Toward the end of the third part, we talked about some specific statistical techniques that we could use under certain restricted situations. Today we're going to shift gears a bit and talk about techniques that we can use even when the data are not well behaved. They're not quite as sophisticated as some of the other techniques, but they're very useful. In fact, I recall having used a lot of these techniques very effectively in my work. We're going to begin by talking about descriptive statistics, and in particular, I have chosen three of the most useful kinds of descriptive statistics to talk about. And then we're going to talk about correlation, and then we'll wrap up by a few examples related to graphing and some of the experiences I've had with people trying to show graphs of things that were misleading. I remind you once again that there's a lot more material on this subject than I can cover in these webinars, and the book that I use as a basis for a lot of this is referenced right here if you want further information. Okay, let's start talking about descriptive statistics. The term descriptive statistics refers to a class of statistical techniques that can be used to describe or show or summarize data in some quantitative way or visual way that is meaningful to us. And this is really the idea. Can we understand what the data are telling us? And a good example of what descriptive statistics can be used for is to show patterns or to show comparisons. And very often that's what you need in order to draw a useful conclusion. Descriptive statistics are not developed on the basis of probability theory, and therefore they don't have to have a number of the assumptions that apply when you're doing many of the statistical techniques we talked about in Part 3. A couple of examples, I talked about this one earlier in one of the earlier parts, student grade point average. It gives you a good idea of how well a student is doing, even though it is mathematically speaking not a very accurate measure. And we talked about some of the reasons why it's not. Another good example is batting average for a baseball player or scoring percentage for an athlete. Anybody who follows an athletic type of activity knows that batting average or scoring percentage is an interesting percentage to keep track of, but it's not the whole story, and that's really kind of what we're talking about here. Now, when we do descriptive statistics, we do make use of a lot of the tools that we've already talked about. For example, central tendency measures. We talked about what they are and when they could be used and what kinds of things would allow you to use them, what kinds of situations you could not use them. For example, if you don't have a ratio scale, you can't compute a mean. We also talked about measures of variance, variability, and those kinds of things. And to the extent that they are valid, that is, to the extent that we have the right kind of a situation where we can use these things, where we can calculate them. In other words, when our scale is suitable, then in fact we often do use them in descriptive statistics. You'll notice in one that's coming up that we use the median quite a bit, and that, of course, requires that you have an ordinal scale or higher. These are some of the most common graphs that are used in descriptive statistics, and we're going to talk about the first three in this webinar. We won't have time to cover all of them, or actually the first four, except the fourth one is really more related to correlation than the graph, the chart. But the idea is that there are certain ways of displaying data that can be very insightful as to what's going on. Let's begin with box plots. I was introduced to box plots early in my career and found them to be tremendously useful. Box plots are a way to illustrate the data using a technique called median and quartile. And the basic idea is we don't have a ratio scale. We don't have normally distributed data. What can we do to try to understand what the data are telling us? And this is a very common situation with software engineering data, which is why I found it very useful in my career and why I chose it for this webinar. The assumption that you make with box plots are that the data are on an ordinal scale or higher. Now, an ordinal scale is fairly common with software engineering. And the idea is, since you have an ordinal scale, you can determine the one in the middle, the median. And then once you divide it in half, you can find the midpoint of each of the halves. So you can divide it into quarters. And this is an example of a box plot. You notice there's a median, there's a first quarter, there's a third quarter, and then there's the minimum and maximum. Now you'll notice that it's not symmetric, and that's one of the interesting things about box plots. This is undoubtedly not normally distributed data because the median is not in the middle, but it's a very good example of how you might utilize a box plot. In this case, we're measuring temperature and the median temperature in some situation or whatever. Some terminology here. The box length is the term used for the distance between the first quarter and the third quarter, essentially the middle part of the box. And the minimum and maximum are called tails. They in a sense, represent theoretical limits. If it were normally distributed, I'll explain exactly how that is determined in a moment. But the way you draw a box plot is you determine the theoretical limit, and then you look at your data, and then you truncate the tails to wherever your data actually turn out to be. If you had a normally distributed situation, or a situation where the mean was defined, in other words, a scale where the mean was defined, then the theoretical limit is approximately 1.5 times the length, plus or minus from the mean. Now, let's talk about that theoretical limit just briefly. The theoretical limit is based on what it would be in a normal distribution if you wanted to go 99% confidence. We talked about confidence levels before. And so the idea is you compute approximate, it's not quite 3 sigma, it's slightly less than that you compute. And that determines the theoretical limit of your tail, enough to give you 99% confidence. But of course, box plots are often used when the data are not normally distributed, so they aren't nice and symmetrical like the one shown on this slide. And another point I want to make is that these are sometimes called box and whiskers plots because the 2 tails kind of look like the whiskers sticking out from the edge of the box. The term outlier means a point that's outside the theoretical limits. And an outlier represents some data that you measured that doesn't fit the theoretical model, which of course you can expect to see happen when you don't have normally distributed data or a nice ratio type scale. Theoretical models, of course, don't always reflect actual data, so outliers are very often real data points that you need to take into consideration. On the other hand, outliers sometimes represent bad data, and therefore one of the reasons you focus on them is to say, is this really good data? Box plots are typically not symmetric. Here are a couple of examples of different shaped box plots. Here's a few more. You'll notice they can be horizontal or vertical, and sometimes, as on the one on the right, they put that little thing on the end of the tail to make it look like a T. Now, an interesting thing about drawing box plots is that they're fairly easy to draw by hand, but until recently they were very difficult to draw using Excel because they weren't one of the Excel chart formats. They corrected that in Excel 2016, but if you are using a version of Excel older than that, it may be a challenge to draw a box plot. There's various websites that tell you how to draw box plots in particular versions of Excel in case you're interested. Now, what can you tell from a box plot? Here's one I pulled off the web that's from a German website, and I think it has something to do with height of people, men versus women or something, but I'm not sure exactly what it's telling, and it's not really terribly important. Notice how different the 4 box plots are. One of the things you can tell is whether the data are symmetric. You'll notice that the second one, the green one with the median roughly in the middle, is pretty symmetric, although it has a bunch of outliers there. You'll notice all the outliers. But most of the other ones are skewed one way or the other. And, of course, you can tell whether or not you have a lot of outliers, which might be useful to know given your situation. One of the most common uses of a box plot is to spot differences. For example, you measure something several times, look at the normal behavior, average things out, and say, okay, this box plot represents our normal situation. And then you measure later to see if there's anything different, so you can tell whether there has been a change. It might be an improvement, it might be a degradation. The point is it's different. The median may have shifted, the box shape may have shifted. the number of outliers, the nature of the outliers, that tells you something has changed. And that's one of the most common uses of box plots, to say, this is the way it used to be, this is the way it is now. Here's a little example. Imagine a professor has a course, and he teaches it every Wednesday, and he does a box plot of his student grades. Now, the little red box in this example represents an outlier. And he has a very symmetrical box plot with a mean grade of about 82, and this is a pretty rough grading professor because very few students get above 90 in his class. But nevertheless, just for illustration purposes, let's suppose that the professor's class is very popular despite the fact that he's a tough grader, and so they add a Monday and a Friday section. So the professor then computes the box plots for the Monday and Friday sections and sees the following. Notice all of a sudden things are very different on Monday and Friday than they were on Wednesday. On Monday, students do better. On Friday, they do worse. And the median changes on each of those days, and it's not symmetrical on either Monday or Friday, whereas it was on Wednesday. So this gives some insight as to what's going on. Even though the data are not normally distributed or don't necessarily have the characteristics we want them to have for more sophisticated statistical techniques. Here's an example I pulled off the web that shows a very common use of box plots, namely for comparing different alternatives. In this example, they are comparing the mileage of different kinds of vehicles. So you'll notice that the SUVs, the one on the left, are very symmetrical, and they have a fairly reasonable but low range. And then the sedans tend to get better mileage, but it's not as symmetrical. And there are quite a few outliers, and so forth and so on. And on the far right, you see the hybrid cars have much better mileage. And in this particular box plot, the diamond represents the mean because this is a set of data where you can compute the mean, and therefore the line represents the median and the diamond represents the mean. But that's only done if you have a situation where you are allowed to compute the mean. Okay, so this is just another example of a box plot. We used them all the time at Raytheon and Texas Instruments when I was there, and I found them quite handy. Another use you'll see of them is stock reports. Very often people reporting on the price ranges of stocks on a day or a week or something will use box plots. Okay, now we're going to talk about bar charts and histograms, which you're probably very familiar with, but maybe not some of the specifics that I'm going to address. Bar charts and histograms are often confused. They look very similar, but they have different purposes. A histogram is used to show distributions. We use them in Part 2, where we introduced the idea of statistical distributions. They plot any kind of quantitative data where the ranges are grouped into some sort of categories or bins. In other words, discretized data. The bars are in a specific order, and you cannot reorder them. And although we didn't do this in Part 2, it is normally the case that you show a distribution using a histogram. We used a bar chart in Part 2. But when you use a histogram, the way you tell that it's a histogram is that you don't have any spaces between the bars. And that's a convention. It's not a requirement, but the convention is that if there's no spaces between the bars, it means it's a histogram, and that tells you may not reorder the bars. Bar charts, by comparison, look very similar, except there is space between the bars, and these are used for plotting categories, as we'll see some examples coming up. And the bars are allowed to be reordered with no significant effect on the meaning of the graph. So here's some examples of bar charts. Many different examples here. The idea of a bar chart is to take a small number of categories and compare them in terms of some value. And they're very handy for that. You're probably so accustomed to seeing them that you never thought much about it. Here's a slightly more complex example of a bar chart where when you see the ones with no spaces between, that means 4 different subcategories, as you notice the little key at the top. What they're doing here is they're looking at load time for various websites based on which tool you use to access the website, or pardon me, which website versus which mechanism you use to access the website. And the idea is that it's telling you a lot of useful information, and it's comparing the different websites here. Now, here's another form of bar chart you may be familiar with. This is called a stacked bar chart, where you're trying to show relative proportions of different things, and therefore you can put them on top of each other instead of side by side, as we did on the previous one. On the other hand, one of the mistakes people make with bar charts is they start making them so complex that it's really hard to understand exactly what message they're trying to give you. And I pulled this one off the web to illustrate the kind of confusing bar chart that sort of people overdo it sometimes. So if we compare a bar chart and a histogram, the bar chart is for comparison. The histogram is for showing distributions. The bar chart is for categories, different colors of cars, for example. The histogram is for some quantitative data that's been discretized. The ordering is arbitrary for a bar chart. It is important for a histogram. Now, I didn't get into it in this webinar, but there's a type of bar chart called a Pareto chart where you do sort the bars in a particular way, but I'm not going to get into that here. The spaces are between the bars are the thing that tells you normally whether it's intended to be a histogram or a bar chart. Okay, now let's talk about control charts. A control chart is intended to be used for tracking performance over a long period of time. And you'll notice in the upper right-hand corner there, it kind of looks a little bit like a highway, and I'm going to explain more about that on the next slide. The idea of a control chart is you're tracking something you're tracking, number of tests complete per week, number of errors found by customers per month, number of lines of code produced per day, performance of the web, whatever it might be. You're comparing it on a daily or weekly or hourly basis or whatever it is, and you're trying to see, is this behavior normal or is it out of range? The idea is to show your actual value compared with some average, perhaps average of previous values. And then there are things called control limits, which are the limits above and below the average that you're not supposed to exceed or go below. The average and expected variation are based either on data from previous projects or on statistics, as we'll be discussing in a moment. Here's a typical control chart. We'll look a little closer. Again, you notice it looks a little bit like a road, and the idea is the blue line there in the center is the average, and the lines that are black in this particular example are like the white lines on the edge of a lane of a highway where it says you're not supposed to go outside those lanes. The red lines are the you're in danger if you go here. This is like the physical end of the highway. And so the idea is as long as you're between the black lines, you're okay. If you get outside the black lines, you're in trouble, and you better start doing something, making a correction, or you're going to be in real trouble. If you go outside the red line, then you're in real trouble. That's the idea of a control chart. Let's look at the terminology. You have an average, and by the way, I should point out that people use control charts for many things. They've been around for about 100 years, and the terminology is not always the same. Different people use slightly different terminology, so I'm going to introduce some terminology here. The upper specification limit is the largest value permitted in normal behavior. In other words, if you get above that red line, you're doing something very abnormal. And normally in a business type situation, that means there's something noteworthy that you ought to take action to do something about. And maybe it means you're in trouble. The lower specification limit is the limit on the bottom. Same sort of thing. Now, the ones that you pay a lot of attention to are called the control limits. It's the point where you take action if you see something that is not good. And there's an upper and a lower control limit. The idea is that the control limits are like the white lines at the edge of a lane on a highway, whereas the red lines are like the physical end of the highway. Think of it as a garage, and the average is the middle of the not garage, a driveway. Think about you have a one-car width driveway, and you have painted white lines on the sides of the driveway so you don't go off the edge, and the green dashed things represent those white lines to say you're getting close to the edge, and the red line says you're over the edge, you're not on the driveway anymore. And that's the idea of a control chart. One of the ways you use this is, I like to use the example of a mother who is doing something in the house and her children are in the next room, and she knows that if it's too quiet, there's a problem. If it's too noisy, there's a problem. And if it's somewhere in between, then it's okay. Or you go to a physician, and the physician is checking something like your blood pressure, and he says, well, as long as it's between this range and this range, it's okay. If it gets above this number, then we better start taking action, maybe having you take blood pressure medication. Or if it's too low, similarly. And if it gets above the red line, then we have to send you to the hospital. You got a real problem here. So that's the idea of a control chart. Now, one of the questions that always comes up is, well, how do we know what those control limits would be? Well, you figure it out by recording actual data, collecting data from whatever it is you're doing, and you establish what's known as a capability baseline, or sometimes just called a normal range of values. It's what is normal. An example, your physician knows what is the normal range of temperature for a person who is not ill. And they tell you, well, it's 98.6. Well, that's not necessary. That's the average, but there's a range about that is a reasonable range for normal people to be. And you gather that kind of information from your actual operation. So, for example, if you are developing software, you might be measuring how much code you produce per week, and you might have a range of what's normal or something like that. You can improve things to get better, and one of the things you do is you make things better and then see whether the normal range has changed. You can establish what are called a desired range of values. You can say, well, this is what we do today. That's our normal range of values. This is where we would like to be in the future. We would like the numbers to be better, or we'd like them to be whatever. If you're interested in more about this, you can look up a topic called quantitative process management at the CMU Software Engineering Institute website. It's a fairly well-established concept in the professional software development community. Okay, now how do we set those control limits if we don't have data from previous projects or whatever? Well, another method often used to set your initial limits is based on statistics. You assume that it's normally distributed data, and then you compute the standard deviation, and then set your limits in terms of the standard deviation. And this little table will help you decide where you want to set your limit. If you set your limit as 2 standard deviations, it means 95% of the time you'll be within the limits, and 5% roughly you'll be outside the limits. If you set it to 3 standard deviations, it's 99%. And the idea is if you don't have any real data to work from, then you can use this technique to give you a starting point until you collect enough data to know what your normal range is. Here's another way of looking at it. You draw your little highway, so to speak, there, and then you determine your standard deviation lines, 1, 2, or 3 standard deviations from the center line or the mean, and decide which of those is more appropriate for my situation. Once you've done this, then you can track progress, and you can know under what circumstances should I take action and on what circumstances should I leave it alone. In other words, there's normal amounts of variations that you can ignore, but when things get out of hand, then you have to take action, and the control chart tells you it's time to take action. That's why they are used, and they're often very, very valuable. We used to use them for looking at the failure rates of projects. We would look at customer complaints, and if they were within a certain range, we knew they were normal. Now, we wanted to make them better, but at least we knew they were normal. And then if we got outside the limits, we knew something funny was going on. If it got too high, we knew there's something wrong with our product. There's a lot of complaints about it. And if the number got too low, we knew there was something wrong. Either nobody's using it or something, because we normally would have more complaints than this. Either way, we would investigate and try to understand what was going on. Now, before I leave this topic, I want to just compare box charts and control charts. Control charts are used for tracking on a regular basis. And you'll notice the one I have illustrated here goes down. That might be a situation where that's perfectly normal because you have been making improvements in something or other. In fact, this is an example from somebody who's keeping track of their weight, and they're noticing that every week it fluctuates, but it's trending down, and in their particular example, maybe they want that to be the case. You can see how things change over time, and you can spot trends. Box charts are used for comparisons. Usually they're used on an irregular basis, and you can see how different situations differ. So they are both very useful techniques. Now we're going to talk about correlation. The idea of correlation is two variables appear to have a relationship, but do they? Well, that's what correlation is all about. Here's an example. The number of students in the classroom goes up, then when there's a break, it's noisier. It's a correlation that I've noticed. When you take more time to write your code, you don't have as many bugs. When the professor gets older, he's more likely to have gray hair. Now, a scatter diagram is the typical way to show a correlation. It's a way to show whether or not there appears to be a relationship. For example, here's a scatter chart. You take two variables and you compare them against each other using an XY chart. And in this example, there doesn't appear to be a correlation. On this example, there appears to be a very strong correlation. Specifically, it would appear that there's a linear correlation, that the relationship is a straight line. And in this case, there's a way you can calculate what the straight line is. It's very simple. B is the point where the line crosses the zero, and A is the slope of the line. Now, here's a case where there appears to be a correlation, but it's not a straight line. And in this case, you have to come up with an equation that fits this data. And there would most likely be a fairly conventional, a fairly simple mathematical equation that would fit that data. We talked earlier in the course about finding continuous functions that fit distributions. Well, the same principle applies here, except in this case, we are finding an equation, a linear or, continuous function that shows the relationship between the two variables. Now, one of the most interesting situations with correlation, and one that I encountered quite often in my work in industry, was the case where there doesn't appear to be a correlation, but then you look more closely. Now, let's suppose you are comparing two variables here, and there doesn't appear to be a correlation. But suppose that was the case because we hadn't looked closely enough. Sometimes what you want to do is you look at your data and you say, is there some kind of categorization of the data that might give us a different picture? Suppose that last diagram showed fault density in delivered code versus how late you were in shipping the product. And you say, well, there doesn't appear to be any correlation. But then somebody says, yeah, but we have two different kinds of projects. One kind does very extensive walkthroughs and inspections as part of their process, and the other one doesn't. They just do testing. And you say, well, is there any difference between them? Well, suppose we categorize the data into those two categories, and then we discover, hey, guess what? The walkthrough ones have the red dots, and the test-only ones have the blue squarish dots. Hey, now we all of a sudden see that there are correlations in the data. It's just that we had to categorize it in order to see it. Correlation doesn't necessarily mean there's an actual relationship, however. And one of the best examples I found is this one, computer science doctorates versus revenue generated by arcades in the U.S. Now, unless there's some weird relationship where CS doctorate students go to arcades, I can't imagine why there would be a correlation between these two, yet there is. And the source at the bottom you'll notice there is a website of a person that specifically tries to find what they call spurious correlations. Correlations that are not real. They don't indicate a causal relationship, but they do show a correlation. And this is a very useful thing to keep in mind, because very often one of the things that really irritates me in politics and in the legal system is that very often the general public doesn't understand the difference between correlation and causality. And so the fact that two things are correlated doesn't necessarily mean that one causes the other, but we tend to think it does. And sometimes it does, but a lot of the time it doesn't. Anyway, let's talk about correlation a little more. We're going to talk about several different ways of understanding whether or not things are correlated and to what extent they are correlated. The first two we're going to talk about are called measures of association, and due to limitations of time, I'm going to have to go through them a little quickly. And for that reason, there is an appendix to this material that I'm not going to show today that talks more about the Spearman Coefficient. If two variables appear to show a relationship, then we hope that this will tell us that there's some way to use that information to predict future behavior. That's why we care about correlation. And as we saw a couple slides back, correlation does not mean causality. It just says there might be a cause, there might be a relationship. And even if there's no causality, there could be a relationship. They could both be being caused by some third factor. But given that, one of the things we try to do is to say, well, are these really correlated or not? One of the ways we decide that is through something called a measure of association. And there are several of them. This is actually a table you saw in a previous part of this webinar series. These things on the right are techniques for measuring how good is the correlation. And you'll notice that one of the key factors here is it a normal distribution or not? There's some other factors that I won't go into now. But remembering that association and correlation doesn't necessarily mean causality, but nevertheless there could be correlation. So suppose we're comparing two variables, and these are all the different things we need to do the calculation. I'm doing this rather quickly, simply because our time is running low. But the point is, this formula gives you a number between -1 and +1 using the variance and the mean and all that other stuff that we talked about. Obviously, we can only compute this one if we have the kind of scale that allows it. In other words, a ratio scale. But what this means is, if it's +1, we have a perfect linear relationship. If it's -1, we have a perfect negative linear relationship. And if it's 0, it means no relationship. So in this example here, the one on the left is a negative relationship. It says, how much is your car worth versus how much mileage? And as you'd expect, the more mileage, the less your car is worth. The one on the far right is in your car insurance costs versus how many accidents you've had. And again, there's a correlation there that's on the +1 side. That's how you use the Pearson coefficient. Now, I talked about being robust. Well, the Pearson coefficient only works if you have very well-behaved data. So what do we do if it's not so well-behaved? It's not normally distributed. It doesn't have a ratio scale. Well, then we can do what's called the Spearman coefficient. And the idea of the Spearman coefficient is it's the same thing, except it's computed on the rank of the values rather than the actual values. And instead of answering the question, is there a linear relationship, it is asking, is there a monotonic relationship? Now, the idea is, in these both examples, you can sort of see that when one goes up, the other one tends to go up. When one goes down, the other one tends to go down. That would be an example of a very positive Spearman correlation. Here's a perfect Spearman correlation. Whenever x goes up, y always goes up, even though it's not at all a straight line. So the Pearson correlation is not 1, but the Spearman correlation is. Pearson says it's not really linear, although it's 0.8. It's not too far off of linear, but the Spearman says it is monotonic. Here's one where they're both low, meaning it's not correlated either way. Appendix A tells you how to compute the Spearman coefficient. Okay, here are some other measures of association that we won't have time to discuss. Now, you may remember again from Part 3, we saw the bottom half of a table we showed in Part 3 talked about using an equation to determine whether or not there's a relationship. Well, the idea of regression is to find a continuous function that represents the relationship or the correlation between the two variables. Linear regression is where you try to find a straight line. And then there are other kinds of regression, as you'll notice here, for other situations. So here's an example of a linear regression situation. You have a bunch of data points, and on an XY chart, they are more or less in a straight line. Linear regression is basically a numerical analysis technique for figuring out what is the closest straight line that comes closest to fitting all that data. And you can figure out the equation for that line using a formula that's in Fenton. I didn't have time to go into it today. This is an example of multivariate regression. In this case, there are 3 variables, and instead of a line, in this example, you have a surface that represents the correlation between the variables. And if you want more on this, go back to the Fenton book. Okay, now our time is just about up, so I want to wrap up today's session by talking a little bit about graphing data. Graphs are commonly used in all sorts of situations, and they're very useful. You don't have to see the numbers to understand what the graph is telling you. Here's an example that comes up all the time. Here's your plan. There's your actual performance, whatever it is you're doing. And, of course, you get into a meeting and somebody yells at somebody, and then they say, well, how are you going to catch up to the plan? And say, well, this is what we hope we're going to do. And being realistic, you say, no, it's more likely you're going to do what that likely line looks like. But the point is, you can figure all this out very quickly by just looking at the picture. And graphs are very useful for that. But the problem is, here are some of the uses for graphs. The problem is graphs are easily used to mislead. And this is one based on a situation I was in one time where some people were trying to convince us to use a particular compiler, and they showed this graph. And it reminded me of graphs I sometimes see in the newspaper or on advertisements comparing options. It's a bar graph. It looks as though option 3 is significantly better, but notice that there's no vertical scale. Well, let's put the scale there. Hey, wait a minute. There's not much difference between option 1 and option 2. The previous slide is exactly what Microsoft Excel produced when I gave those 3 numbers. It tries to exaggerate the differences. Well, what if you put a more honest scale next to it? Here's an honest scale going from 0 to 120. You'll notice that for all practical purposes, there are 3 equal options. This illustrates how easy it is to mislead using poorly thought of graphing techniques. Now, if it were a race, you might need to know the difference. But next time you see a bar graph in a newspaper, look at the vertical scale and say, are they being honest or not? What are they really doing? Are they correctly focusing on something minor, or is it really important? Another way to misinterpret or maybe to get more out of graphs is to assess the data by categorization. We talked about categorization before in terms of correlation. Well, consider this scenario. Here's a graph of uncorrected defects. And you show that to the boss, and the boss says, things are really getting out of hand. But what if you show it this way? You have 3 categories of data, and you show the defects by each category. Now, all of a sudden, you draw a different conclusion. The important defects are being handled properly. We just don't have enough manpower to get all the defects done. That's a very different message. Okay, so to wrap things up, I just want to comment that when you're doing graphs, you need to pay a lot of attention to what is the right way to draw the graph, and so that we interpret it correctly. I've been in too many business meetings where people saw a graph and draw the totally wrong conclusion because of the way it was drawn or the fact that they didn't understand how to interpret it. Categorizing things requires skill and judgment, and very often one of the problems is that the way the engineer sees it isn't the way the customer sees it, as is illustrated by this little diagram here. So you have to give a lot of thought to those issues. Okay, well, we're at the end, and it's time for questions, and I will point out that there's going to be a feedback file produced for this part, as there has been for all the previous files, or the previous webinars. It will be put up there later this week. And I will take all the questions I can answer now, and then I will try to answer all the questions along with perhaps some additional information in the feedback file. And let me just also mention that in the Part 2 and Part 3 feedback files in particular, we got into some interesting topics that we didn't have time for in the webinar, that we sort of put a lot of information in there that wasn't in the webinar. For those of you who are interested, you might want to take a look. Okay, Robert, time for questions.
All right, thank you very much. So our first question, when we consider ordinal data, would you think that box length is a meaningful measurement?
Well, is box length a meaningful measurement? Well, the box length is probably not a meaningful measurement for ordinal data, but it does, the physical shape of the box tells you where the first quarter and third quarter mark are, and that's really about all it tells you. And you're right, the box length doesn't tell you, other than if you noticed that when it was normally distributed data, the box length was relatively small compared to the totality of the whisker. In other words, the box was relatively small and the whiskers are quite long. That tells you that your data kind of looks almost normally distributed. Whereas when the box length is large and the whiskers aren't that long, that tells you something very different. It says it's probably not at all normally distributed. So there's some things you can gather from that. But you're right, it's not, well, again, these are robust statistics. Numerically, some of these numbers aren't necessarily all that meaningful, but you can still kind of get a message from the box.
Okay. So when we look at slide 23, which I just changed the slides to, you showed a bar chart here that was normalized. Can you talk a little bit about what are some of the pros and cons to normalizing bar charts in this manner?
Are you talking about stacked bar? You said 23. Which slide did you?
Sorry, 22. The slide that's shown right here, 22.
Okay. Well, in this particular example, apparently the black line represents some product they're trying to promote here called WebKit. And quite frankly, I brought this one up to show the idea of showing multiple things side by side. I really don't have any thoughts at the moment on normalization, but I will look it up and put something about it in the feedback file.
Okay. And could you give some hints or tips on how to persuade people that might be skeptical within your organization on the importance of the issues you've been talking about?
That's a really good question. We certainly had plenty of examples when I was working of situations where people didn't pay attention to the issues that I'm talking about. For example, the one I just showed a few moments ago about trying to sell us a compiler and convincing us it was so much better than the other ones, when in fact, when we looked closely, we saw that it wasn't. The most effective technique I encountered was when you could use the facts that we've talked about here to make a point that showed that you were avoiding a big mistake. And that compiler was a really good example where we were able to show our boss that it wasn't really that much better and it had been exaggerated. The various other kinds of examples, sometimes what you have to do is you have to say, pretending that the mean exists when it doesn't is something we have to explain to the boss so the boss understands why we want to do it a different way. An example that I run into quite often, and it's one of my favorite examples, is the one where people say the average U.S. citizen makes so much money per year. And the problem with that is that that's not a normal distribution. It's a very skewed distribution. And the mean or average is considerably higher than the median and even higher than the mode. And when people say, yeah, the average person makes so much money, yes, sometimes you just have to explain with numbers. The most success I have had is when the boss is willing to listen. And when you can make your case and you know what you're talking about and can show an example and can show, here's what the truth is. If you are unfortunate enough to have somebody who's making decisions who's not willing to listen to facts, sometimes you just have to say, I'm in a Dilbert cartoon and I'm going to have to put up with it. But one of my favorite examples was when we were able to convince the people who approved acquiring of capital equipment that we were losing $10,000 a month because they hadn't approved something, and we were able to show that if they would approve it, we would save them so many $1 million a year. You have to find ways to communicate the facts in the language of the person you're trying to convince. And sometimes that means you have to understand what matters to them. Sometimes what matters to them is not what matters to you, but you have to find a way to communicate it in ways that matter to them. There's another technique we used one time that was very successful. We were trying to convince our boss to adopt some of the Software Engineering Institute's recommendations, and the boss thought they were stupid. So we found a way to get the boss invited to attend a Software Engineering Institute week-long executive seminar. And then he came back trying to convince us to do all the stuff we'd been trying to talk him into for the last 6 months. But sometimes you just have to get clever about it. But knowing what you're doing helps.
So in your opinion, how big should an organization be before these kind of techniques actually become meaningful? And specifically, does the notion of sample size play into that?
Well, certainly a small organization may not have enough data to be able to draw a lot of conclusions, particularly using conventional statistics, although things like the ones we showed today, like Boxplots, for example, may still be very useful. It is true that you get a lot more out of data when you have a lot more data, and there's just no way around that. How large? I guess the way I want to answer that question is to say it's always worthwhile to understand these things. Whether or not you have enough data to justify using any of these techniques is something you have to judge for yourself. But some of the robust statistics can be used with relatively small amounts of data. Again, I go back to Boxplots because I found them so handy. Certainly things like when you get something like a control chart, if you don't have very many data points, you can't establish what your normal range of behavior is. So you need to have more data points in order for that to be useful. But again, knowing the principles will help you decide, here's a situation where this concept can be applied.
So during your tenure with Raytheon, what would you say was the most common type of distribution of data that you saw?
The most common type of what? I left.
Data
what
distribution.
Was the word before data?
Distribution.
Distribution. Oh, I don't know that I could say. I saw an awful lot of non-normal distributions. An awful lot of them were. On the other hand, we had a lot of data. Raytheon's a big company. And what we often, for example, we could compare data from one facility with another facility, or one division of the company with another, or one project with another project. And we often found that the distributions were similar from different parts of the company, but one might tend to be larger than the other or something, and that would lead us to figure out what are they doing differently kinds of things. But I don't know that I could put my finger on any most common type of distribution other than to say that normal distributions weren't very normal.
All right. I'm afraid we've run out of time today. Thanks again to Dennis for his informative presentation and insightful answers to the many questions. Special thanks to each of you for taking the time to attend and participate in today's webinar. This webinar was recorded and will be available online in a few days at www.sigsoft.org/resources/webinars.html. You can find announcements on upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and www.sigsoft.org. On behalf of SIGSOFT, the speaker, and myself, thanks again for joining us, and I hope you will join us again in the future. This concludes today's webinar.